Now we will look at some operations on point processes. So first one is the translation shift of a point process. So let X be a vector, and if point process phi is made from point xi, then the shifted version of this point process is, which we denote by phi x, is xi plus x. So you take each point and you shift by x. So the new point process you will get is the shifted version of the PP. Okay, so you do it for every realization. You take one realization, you take all points and shift it to x, and then you take another point, another realization, you again shift all points. So the corresponding random corresponding random object you get is the shifted version of it. And then you can understand that the probability of the realization are mapped in a way that uh, if you take some realization phi and you shift it, and phi has some probability of occurring, then the shifted version will have the same probability of occurring for the new PP. So this operator we know as the theta x, and when we say that theta x is applied on phi, this means I will get a phi x. So consider realization phi. Now shift each point to this realization phi by x. So add x to every xi to get a set of new locations. Original realization of PP is this, and the shifted realization of PP is this. So whatever is the probability of this phi will be the probability of this phi x for the new PP. So you can see there this diagram also. This green ones are the old realization, and you shift it by a vector x to get the new realization. Now what will be, this is from the set notation, what will be the equivalent representation in the measure? So if B some set, what will be the phi x of B? I mean, how many points will be there in the set B for the new shifted PP? So you can look at this is a new shifted PP, and suppose this is set B, and I want to understand how many points are there. So when I compare it with the older unshifted version, I see that if I set shift this B by minus x, then if this arrangement will look like this arrangement. So in this case, if this set has 1 point, this in the shifted version, the B will have 1 point. If in unshifted arrangement, B minus X has 2 points, then in this case also set B will have 2 points for the shifted B. So whatever is happening in this set B minus X with respect to the unshifted version or the original version, same thing will happen in the set B here for the shifted version. So you can clearly see that the number of points in set B for the new shifted PP is equal to number of points of the old or the original PP in the set B minus X. So this is the result again. Phi x of B is equal to phi B minus X. And note that what is B minus X? B minus X is made from all vectors by taking vectors in B and then shifting it by minus X. So it is made from all y bars, as that y bar is equal to z bar minus X, where z bar is each element of P. And if I take expectation on both sides, this will become lambda x of B is equal to lambda B minus X. So if I want to relate them, the new intensity measure is equal to the old intensity measure of the shifted set B minus X. Now let us understand what is a translation on event. Recall that event is a set of point configuration satisfying certain property. Right? For example, I said event that there are 3 points in a ball of radius 3 at the origin. This means it refers to all point configuration, all point process realization where this property is satisfied. So now we will define translation operator over this event. Consider an event E, then define EX as made from all realizations such that phi minus X belongs to E. It means phi minus X has the property E. Okay, so EX is made from all realizations such that if you shift them by minus X, then that realization will have property E. Okay, so when I say a point process has property EX, it means its shifted version phi minus X has the property E. So if I want to write it for any event E, define the new event EX by considering all realizations such that their shifted version by minus X satisfy the condition set for event E. So you can understand this. Consider an event, the ball of at the origin with radius 4 has 2 points. Okay, so this is the ball at 0, 4 and it has 2 points. So does this realization has the this property? If yes, then it will be in the set E, and if not, then it will not be in the set E. So here is this case, this is not in set E. Now I want to ask whether this configuration has property EX or not. So in that case, what I do is I first shift it by minus X, and then for this, I will ask whether it has property E or not. So property E is whether this ball has 2 points. So if this configuration, the shifted configuration has 2 points, then I will say the original version has property EX. Okay, so in other words, you can understand either I tell whether this shifted version has 2 points in this ball, or I can also, if I shift it back the original location, then I have to shift this ball also by X. Then I can answer whether the original version has 3 points in this set or not. And this set is what? This set is nothing but this ball shifted by X. So in other words, by saying event EX has occurred, I can either look at the shifted version by minus X and see if it has property E or not, or I can look at the new, the original point process and look at the, I modify this property a little bit, right? Instead here, I'm actually looking at whether this ball of at X at 4 radius has 2 points or not, okay? So in this case, how does this will change depend on exactly property. This you have to, this exercise you have to do geometrically. Similarly, next come to the rotation of the PP. If you have a point process, then the phi A is made from rotating xi by rotational vector A. Okay, so you take each realization and shift it by rotate it by some angle, and the new points will be the new realization. Okay, if I want to ask what will be the measure notation, so again, if this is some set and I want to look at whether the new point process has how many points are there for the new shifted version, then I can rotate it back. So I'll get the original one. I will also rotate this rectangle back. And then I have to answer whether this set has how many points are there. Okay. So whatever number of points this set has, the same number of for in the original version. Well, same this set will also have the same number of points for the shifted version. So phi A B here is phi A inverse B. A inverse B, I mean I am rotating B back by opposite in the opposite direction by same angle. And same way you can also define the rotational event and the expectation measure of in the with respect to a new rotated version also. Now, why did I define these two operations? This will help us determine some statistical properties, special properties of PP. The first one is the stationarity. A point process is stationary if its probability law is invariant to the translation. It means if there is some event E, then the probability of E is equal to probability of US. Okay. And let us remember again, E is some property and EX is that you shift the point process by X minus X and then ask whether it has a property E or not. Okay. So if I take a particular property and compute its probability, that what is the probability this property will be satisfied, or if I ask that the shifted PP will have this property, what is the probability of that? So both, if they are equal for every value of x, then we say the point process is stationary. It means it does not change when you shift the point process. So this basically means that probability that the PP has a particular property does not change if you shift each point of point process by a vector x for any value of x. This also means translation of origin does not affect the probability law. Okay, if I take origin somewhere else, it should not change my probability law. And also the intensity measure is translation invariant, because if you shift the point process, the distribution is not changing. So the intensity measure should be translation invariant. It should only depend on the size of the set, not where it is located. Okay, so this just means that the phi x of b is equal to lambda x of b for any set is equal to lambda b minus x, and that should be equal to lambda b. It does not depend on the location of the set. Again, note that this condition that the intensity measure is translation invariant is a necessary condition for stationary PP, but is not the sufficient one. Which means if a point process has translation invariant intensity measure, that does not mean it will be stationary also. Okay, so if something is stationary, the intensity measure does not depend on the location. But if the intensity measure does not depend on location, that does not mean the point process will be stationary. Okay, an example of such is, consider a point process which is binomial on the one side of y-axis and the Poisson on the other side of axis. So in that case, intensity measure, no matter where you take, it will be same, because I'm choosing binomial Poisson such that the intensities are same. But if you take a rectangle in the first space, it will the distribution will be binomial inside, and if you take the set in the other side of the axis, you will see the points inside the Poisson. So distribution will change, but the mean number of points will be same. Now, what is isotropy? Point process is isotropic if its probability law is rotation invariant. It means for any rotation angle theta, the probability of event E and E theta will be equal. Okay. A rotation invariant point process statistically look the same in all directions. And if I rotate all points by theta around the origin, it does not change the probability of any property. What is motion invariance? Is a point process which is stationary and isotropic both, we call that motion invariant. So the distribution will not change with respect to translation and the rotation. Ergodicity, what is ergodicity? Remember, for random process, something is an ergodic random process if the distribution of a single realization over time is same as distribution of all realization at a single time. It means if I look at just one realization and look at over time, it will have all the distribution which you can expect from different realization if I just pick one single time. Similarly, ergodicity for a point process means that the law for single realization of PP at different location is the same as the law of multiple realization of PP at a single location. Okay, this means if I want to compute the number of points in the ball, for example, either I can fix the ball and I can take multiple realizations, or I can put this ball at different location and compute the average in a single realization. that should give me a same result if the process is ergodic. Okay, so in simulation, ergodicity of point process allows us to consider only single realization instead of multiple realization. So this can help in the simulation because this can reduce simulation computation time for us. Okay, so suppose there is a stationary point process and we want to compute the average number of points in a ball of radius r. So let's call LR is equal to expected value of phi B0R. B0 is a ball of radius R at origin. The phi B0 is number of points in this, and expected value will give me the average number of points in this ball. So the conventional way is ensemble average. You generate a realization phi I. You calculate average number of points in this ball, and you repeat the step for multiple realization, and then for you just take the average. So if you have done n iteration, you do 1 upon n and summation over each value, number of points in each realization, and you expect to get an answer which will be the average number of points. And if you want to get it accurate, you will just increase n to infinity. Okay. Another average is way is the spatial average. You generate a single realization of pp in the space. You choose balls of radius r at different location y1, y2, y3 in some area A. And then basically as large as area you take, the better result you get. And they count the number of points in each of these balls. And then you average it over. So if you have taken n balls, you just add the number of points in all these balls and divide by 1 upon n. And as you increase n tending to infinity, you expect to get average per number of balls in this ball. So for ergodic point process, both matter will give the same answer as n tending to infinity and A becomes as large as the complete D space. So first one is the average over n realization, and second is a single realization, but you take different points in A and then you average it over the complete set A. So just to summarize, stationarity means law is translation invariant. Isotropic means law is rotation invariant. Motion invariance means both stationary and isotropic. And ergodicity means the spatial average is equal to ensemble average. So superposition of a point process generally means that you want to take union of two or more point processes. So suppose this is one realization of one point process and this is another. So the superposition would be a combination of nodes from both. So if you use the set notation, then you can just say it is phi1 union phi2. You're adding all the points from phi1 and you're taking union with the new points of the phi2. And if you take the measure notation, then this will be phi1 plus phi2. It means for any set A, number of points in that set is equal to number of points from this one and number of points from this one. So what will be the new density? Consider 2-point process phi1 with density lambda1 and phi2 with density lambda2, and let phi3 equal to superposition of both. Then what is the resultant density? So suppose phi3 has intensity measure lambda3. Then for any set A, lambda3A is equal to summation over all indicator that xi belongs to A. So you add it over all points of phi3, and whatever point says that I belongs to A, you add them, you get a total number of points, and then you take the expectation and get the mean number of points in it. Now, if a point belongs to phi3, it means the point either belongs to phi1 or phi2. Okay, so you can break this integration into two parts. One is over all points in phi1 and then all points in phi2.
And because the expectation linear, I can break this into two summation: expectation of all summation over all point in phi 1 plus expectation over points of phi 2. Now if you look at this, this is nothing but the expectation measure of phi 1 of set A. So this is lambda 1A and this is lambda 2A. So what I get is lambda 3A is equal to lambda 1A plus lambda 2A, and that is true for every set A. So if the density exists for phi 3, let it be lambda 3, then lambda 3A is equal to integration of lambda 3x dx on A. Similarly, lambda 1A is the integration of lambda 1x over A, and lambda 2 and the integration of small lambda 2x over A. Now, since this is true for every A, it means I can take A very small, like interval dx, and then I can show that this means that lambda 3x should be equal to lambda 1x plus lambda 2x. Note that to say this, you need to show that this is true for every set A, which is the case. If A integral is uh, equal for only some sets A, then the does not mean the inside term will also be equal. So this means if you do superposition, the density will add up. And if this is a stationary PP, in that case, lambda A is equal to lambda into A. So in that case, you can say lambda 3A is equal to lambda 1A plus lambda 2A. So it will be, density will be lambda 1 plus lambda 2. Okay. So you get a new point process with the uniform density. The question is, how is phi 3 distributed? That you cannot say exactly, because you have to this is just a mean computation, but if you have to calculate distribution, that may be complicated. It may also depend if the phi 1 and phi 2 are related to each other or not. So you can extend it for superposition of more PPs. If there are n PPs with density lambda I, then the superposition will have density, which is summation over all these densities. Now I want to show that although the previous result is true for any point process, if you have phi 1 and phi 2 both as Poisson point process, there is something more you can say. You can also compute a distribution of the superposition of these two. Okay, so phi 3 is phi 1 union phi 2, and to characterize what is the distribution of phi 3, I'll compute the Laplace function. Recall that if I compute the Laplace function and I can recognize its form, then I can uniquely say what is its distribution. So to characterize the distribution of phi 3, we'll compute Laplace function. Laplace function of phi 3 is given as expectation of exponential minus summation of fxi over all points phi 3. Okay. Here I'm also assuming that phi 1 and phi 2 are independent. So again, this summation can be written as a summation over 2 points, summation over phi 1 and summation over phi 2. And then I can, because it's an exponential term, so I can break into two product. One is exponential of minus over summation over all points of phi 1 and summation over all points of phi 2. Okay. Now, since we assume phi 1 and phi 2 are independent, I can break this product into two parts. One is the expectation of this term, which is Laplace functional of phi 1, and this is the Laplace function of phi 2. Now, if I put back the Laplace function of phi 1, because I know phi 1 is PVP, so his Laplace function is given by this formula. Similarly, Laplace function of phi 2 is given by this formula. Okay. Now, the remaining is to solve it. Because both are exponential, this term will add up, and it's an integral sign, so these and these are common. So what you get is 1 minus e to the minus of x lambda 1x plus lambda 2x dx. Okay, now I know lambda 3x is equal to lambda 1 plus x lambda 2x, so I will replace it here, lambda 3x dx. Okay, so if you look at this, is the nothing but the Laplace function of PPP with density lambda 3. So what you understand is phi 3 is nothing but a PPP with density lambda 3. Okay, so this is a result if you have two independent PPPs then the superposition of these PPPs is also a PPP. And this result is true even for more number of PPPs. If you have n number of Poisson point processes and all are independent to each other, then the superposition of them is also independent. Sorry, superposition is also Poisson point process. The second operation we discuss is thinning. Thinning refers to removal of some points from each realization of point process. So what we do is we take each realization, we go to each point. Suppose we toss a coin. If we get a head, we keep that point, and otherwise we discard it. And whatever the points are remaining, we collect them from that realization. We do it for every realization, and the point process as such we get is a thinned version of the original point process. And here we are doing independent thinning. It means we're going to each point, and whether this point is kept or discarded, that decision is independent of other points. So let us compute the density of the point process such formed. Suppose we go to each point and we do independent thinning with retaining probability P. Okay, which means I retain the point with probability P and discard it with probability 1 minus P, and is independent thinning. It means that thinning decision does not depend on other points. So suppose the original point process has intensity measure capital lambda and density lambda x. Let SI denote the indicator that the point I is kept. So for every I, there is one indicator SI. So probability that SI is equal to 1 is P and is independent of other SJs. Now suppose phi dash has intensity measures capital lambda dash. In that case, lambda dash A is equal to expectation of indicator over all points in phi dash that xi belongs to A. Okay, now this is I'm adding over all points in phi dash. This summation can also be written as in terms of the phi, because all points of xi are actually coming from phi, but only those points where si is equal to 1. So if I add this, do summation over all points of phi, but I add this additional indicator si equal to 1. So in that case, all the points which are not kept, this will be 0, so they will not affect the summation. And all the points which are kept, this will add 1, so they are actually equal. Now, this expectation with respect to point xi and si, because si is also a random variable. But I can take the expectation with respect to si inside, condition on the points. So this is expectation, summation over all points, and then I take the expectation of si inside, because si does not affect other points, and it also does not affect this function. So once I put this is become ESI, expectation with respect to SI of indicator SI belongs to 1. So this is nothing but the probability that SI equal to 1, which is P. And because P is constant, I can take it outside. So this become probability that expectation of over summation over all point that XI belongs to A. And this is nothing but capital lambda A. So this is P into capital lambda A. Okay. And you can show that if expectation measure of the new point process for every A is equal to P into lambda A, then density of this process lambda dash x is nothing but P times the original density. So this is just shows what is the impact of P. So regional density is proportional to P. So if I retain with 0.7, this is the original. I retain. I did a thinning, and all the points which have crossed are retained. So I get this point process. And if I retain with 0.2, I get even less number of points. So as your retaining probability decreases, you get less density in the final output. Now this thinning in the previous case was same for every point. You can do thinning based on the basis of location also, right? So if you do that, because even if you start with a stationary point process, if you do thinning based on the location, eventually the output PP will not be stationary anymore. it may not have constant density. Okay, so we are still doing independent thinning. So let us see what will be the impact of such thinning. Compute the density of phi dash constructed by thinning of the point process phi, where retaining probability for any point at location x is px. So px is a function of x, and if the point location is x, you thin it and retain it with probability px. So assume the original density is lambda x and the expectation capital lambda a. So what will be the density of the new point process? So let's assume the intensity measure of the new point process is lambda dash a. Let SI denote the indicator the point is kept. Okay. Then expectation that SI is equal to 1 is probability of XI. Okay, that depends on the location of the point. So now lambda dash A is summation over all points of indicator as Xi belongs to A, and I add it and I convert it to summation over all points and added this indicator, which in turn becomes probability that Si becomes to 1. Now this probability Si becomes to 1 is nothing but Pxi. So what I get is the summation over all point indicator Xi belongs to A and Pxi. Now if you look at this multiplication is nothing but a function of Xi. So I can apply Campbell theorem because this is summation over all point of some function xi. So Campbell theorem says that this integration will become integration of fx lambda dx. And what is fx here is this. So I put it here, and eventually what I get is integration over a of px lambda dx. And if it has density, then this will be px lambda x dx. Okay, and then you can show that this is true for every set A. So lambda dash A is equal to px lambda x dx for every set A. Now, if the density of the derived PP exists, suppose it is lambda dash A, then we know that for every set A, lambda dash A should be integration of density over A. Okay, this is by definition of density. If density exists, then this should be true. So if I compare this and this, what I get is if the density exists, the new density should be equal to px into lambda x. Okay, now if you look at this, even if lambda x is constant lambda, because of this px, the new point process will no longer have the constant density over space.
Now we will discuss an important result. We will compute. We will take a Poisson point process, and we will do an independent thinning over this process, and we will calculate the distribution of resultant point process. So in particular, consider a Poisson point process, the density lambda x, and after thinning, the derived point process is denoted by phi dash. It is so we use SI as an indicator, and whenever XI is kept, any ith point is kept in the derived PP, we will make SI equal to 1. And if SI equal to 0, then XI is deleted. So the new point process can also be written in terms of old point process in the following way. It has all the XI such that XI belongs to phi and corresponding SI is 1. So if we assume independent thinning, then the thinning of each point is independent to others. So this indicator SI can take value 1 and 0. So this is a Bernoulli random variable. And if the retaining probability is Px, then this is a Bernoulli random variable with parameter Pxi associated with Xi. So if the location of the ith point is Xi, we will have a probability Pxi, and we will retain it. So SI will be 1 with this probability and 0 with 1 minus Pxi. And if it is 1, we will keep that point in the derived point process. So the density of the thin PP will be lambda x Px that we have already calculated. But what we want to understand here, if we take PPP, then what is the distribution of the resultant point process? So to compute the distribution of resultant point process, we will compute it Laplace functional. If Laplace function comes out to be a known form, then we can guess, we can know what is the actual distribution of phi dash. So Laplace functional of phi dash is given as expectation of exponential of minus summation over all points in phi dash of fxi. Okay, and now we know that this summation can also be written in terms of summation over phi by introducing Si. So if I take summation over all points fxi si, the both are same because whenever xi in phi dash comes from xi in phi only, and whenever si is 1, only those points are kept, which will be in phi dash, and whenever si equal to 0, these are not, those terms are not taken here, and also they are not taken here because si is 0. So even if you have this in summation multiplied by si, they will become 0. So the contribution from all the points which are not retained in this is also 0, and this also 0. So they both terms are actually same. Now to further solve it, we notice that this expectation is first in terms of phi, okay, because phi has all the randomness of xi's, and then it also has expectation with respect to si's, okay, and this si only depend on xi. So what I can do is I can break this expectation into two parts. One will be outside expectation of phi, and inside there is a product of xi and the expectation of Si given Xi. Okay, so actually it is Si given phi, but note that Si only depends on Xi. Out of the complete phi, it only depends on Xi. So Si given phi is same as saying that Si given Xi. And then we have this term e to power minus fxi Si. Note that I can remove this product term outside this expectation because of two reasons. One is this expectation with respect to SIs, and SIs are independent across I. So these terms are independent given XIs. So I can take it out. Okay. And second thing, these terms only depend on SI, not no other for a single I. Okay. So now I have want to focus on this one. So if you take this e to power si given xi to power minus fxi si, now given xi, so this xi is constant, this term is constant. Only random variable here is si. Now si takes two values. So the expectation of this is very easy to compute. The expectation will be probability that si equal to 1 e to power minus fxi into 1 plus probability si equal to 0 into e to power minus fi into 0. So that will be 1. So this product term, and this one is pxi, and this is 1 minus pxi. So what you get is e to power minus fxi pxi plus 1 minus pxi. And that is a function of xi only. There is no si left anymore because I have already computed the expectation of si. So this term is just a function of gxi. So if you look at the original expression, expectation of product of expectation of si given xi, e to power minus fxi, and if I replace this by this gxi function, it will become expectation of product of some gxi, where gxi is given by this particular form. So now you can notice that this is nothing but just the expectation of product of function values at different xi points. Okay, so this is nothing but the PGFL of this function. So because xi, this is a PPP, what I know, the expectation of product over gxi is exponential minus integration lambda x 1 minus gx dx. So that is how I got this expression. Now I just put the value of gx here, which is px e to the minus fx minus 1 plus px and lambda x dx. Now I can solve this, at this 1 cancel, I can take px common, so it will become px 1 minus e to the minus fx lambda x dx. Now if you take px and lambda x together, and let's call it lambda dash x, then what I get is Laplace function is exponential 1 minus e to the minus fx lambda dash x dx. And I know that lambda dash x is the density of the new point process. So if you look at this, this is nothing but the form of PGFL of a, sorry, Laplace function of a PPP with density lambda dash. So from this we can say that derived PPE is actually a Poisson point process with this density. Okay. So once again, we have compared with the Laplace function of PPP and found they both are same equal. And in fact, the density, in fact, the PPP with this density will have the same Laplace function. So this will be nothing but the derived PP, which is coming after thinning, is nothing but this PPP with density lambda x only. Notice that it is very crucial that thinning is independent. Otherwise, you will not be able to take the products here, and then the resultant point process will no longer be a Poisson. Okay. So what can be the examples of this? Suppose you have a device-to-device network, and suppose you have a device-to-device network, and then some devices turn transmitter and some devices turn receivers independently of each other. So if I want to look at only the transmitter, only the devices which are transmitters, it is like I'm thinning the nodes, and I'm only keeping those nodes which are transmitter. Okay, and there may be some probability of a device turning to transmitter or receiver. So this new point process having this of transmitters will be an independent thinning of the original point process. And if the original point process is a Poisson point process, then the transmitter process will also be a Poisson point process. So because of this property, it helps us many times whenever we want to divide a one point process, Poisson point process, into two processes of two different types of points, and assuming they have this marking is independent, then basically this result can be applied that both of these processes are actually Poisson point process.